Thank you. Um, Hi, everyone. I'm Mrunal, and I appreciate you all joining my virtual session. Today, I'll be presenting cluster-based tile embedding, a general representation for a level design with skewed tile distribution. The presented work is done with Dr. Matthew Gusdale at the University of Alberta. The domain that we are working with is procedural level generation via machine learning, which is the application of machine learning techniques for automated generation of game levels. While the PCGML community has done impressive research in level generation and blending techniques, I believe we are still far from achieving generalizability in our model design. A primary reason for this is limited data set availability and inconsistency in the current representation practices. And in the presented work today, our broad focus is on learning representations for general level designing in PCGML. So, a popular data representation practice in PLGML model has undoubtedly been the video game level corpus, VGLC. It represents a level as a composition of 16 cross 16 tiles, which is associated with a character representation and a set of affordances. Therefore, if we take the Super Mario Brothers level at the top, it can be represented as a sequence of repeating characters as illustrated on the bottom. However, annotating such clean representations requires substantial amount of effort from domain experts and fan communities, which is time consuming. Therefore, PCGML community would largely benefit from a representation of same quality, but that is done without a human transcription. To counter some of these limitations, we presented tile embeddings at AID last year. Tile embeddings are a continuous domain-independent representation of tiles. They were learned by employing an autoencoder, which takes in the tile and the context information and the affordance information to learn a 256-dimensional embedding vector. And our tile embeddings have shown promise in generating annotated and unannotated games previously. So in the presented work, we extend in this research direction. We begin by testing out tile embeddings for generating Super Mario Brother levels by training an LSTM on it. And the output we got was this. If we dig into what's happening here and suspect representation is the problem, our suspicion would just get stronger if we train the same LSTM network, but on VGLC representation instead. So ideally, the representation shouldn't have been a problem because tile embeddings have shown to work for annotated and unannotated games. So let's uncover the mystery here. The answer is the absence of sampling in the output layer. To understand what I'm talking about is an LSTM on VGLC representation outputs has a softmax activation at the output. So it outputs a probability distribution. And the next tile is probabilistically sampled from this distribution. Whereas an LSTM trained on tile embedding representation outputs a 256-dimensional embedding vector directly. So it always picks the most probable tile at the output. Because of this, it does a greedy selection instead of probabilistic one. This problem of sampling becomes worse when we have cases of skewed tile distribution. So on comparing the distribution of SMB versus that of load runner, we find that SMB has a skewed tile distribution with empty tiles occurring 90% of the times, whereas that of load runner is comparatively more balanced. So when an LSTM is trained on tile embeddings of SMB, it does greedy selection and generates all empty levels. So this research aims to learn a discrete representation, which would allow us to approximate a probability distribution just like it did for VGLC. We do this by employing clustering, but before we get to that, we introduce two modifications in order to make our representations more robust. It includes clustering loss and incorporation of edge information, and then we train our novel two-step level generation pipeline. And this is our system diagram. So I'll give you 2 seconds to look at it. Don't worry if it looks daunting. We'll just walk through it now. We'll start with the autoencoder design. The autoencoder learns to take in 3 pieces of information, just like the original ones. We have detailed out the inputs in our original implementation and in the current one. So I'm going to highlight what modifications we made. So we have added the edge information in this in training this autoencoder. Edge information is crucial to handle cases where affordance information is missing and the clustering solely lies on visual representation. So with original tile embeddings, we found that clustering in such cases was predominantly based on colors, and which was undesirable. Then we train this autoencoder on reconstruction loss and the clustering loss that I mentioned earlier. So we take this clustering loss by computing a data vector prior to training and feeding it to Gaussian mixture models. The clustering loss is then computed as categorical cross entropy based on cluster assignment to the original data vector and the reconstructed data vector. So if we take this autoencoder and pass an SMB dataset level to it, we replace each tile with a 256 dimensional embedding, which we call as CTE representation, clustered tile embedding representation. And the next step of our pipeline is an important one to learn probabilistic distribution, which is discretization of tile embedding. We do this by feeding all the embedding vectors across the dataset to dbScan clustering, which assigns a cluster to each embedding, and we represent it as one hot encoding. This is just to make data parsing easier for the next steps that are going to follow. So the CT representation here, each of the embedding vector is replaced by its clustered one hot encoding, and we get a discrete CT representation. This can then be fed to LSTM, just like we did for VGLC. And on punching the seed sequence, we get new discrete levels. The final piece of this puzzle is to visualize the new levels sampled, but it's not straightforward because cluster numbers do not map one-to-one with the visual representation. To understand what I'm talking, we draw parallel and see VGLC representation. Each character is mapped to its pixel counterpart, and it follows a rule-based translation. But as we can see, it does not follow one-to-one mapping. Therefore, in our model, we train a translation mechanism to convert discrete representation to its continuous counterpart. With this final piece, we complete our system architecture. And next, I'm going to move to evaluating it. For evaluation, we do level generation for SMB and perform ablation study on it based on different representation. So the first one is LSTM trained on VGLC, then on original tile embeddings. And then this is LSTM trained on CTE representation. And this is our two-step level generation pipeline trained on the clustered tile embeddings. So we see substantial improvement as we move from continuous representation to discrete representation. To quantitatively assess our work, we employ 6 tile-based metrics. The first one's linearity, which measures how well the level fits onto a line. Then we have leniency to compute the difficulty of a level. Interestingness, it measures the proportion of tiles that bring visual variety to a level. For playability, we run an A-star agent on the generated levels to see if they are at all playable. Density measures the non-empty tiles in a level. And enemy sparsity is to compute the spread of enemies throughout the level, because a generator can often get stuck in generating strings of enemies, which is again not desirable. If we look at our results, we see the discrete representations consistently outperforms the continuous ones, and the metrics on the continuous representation is nowhere close to the distribution of the original data set. This demonstrates the importance of sampling and our two-step level generation pipeline. It allows our CTE representation to compete with VGLC representation. We find this results valuable because VGLC benefits from hand authoring. As our next evaluation, we generate levels for unannotated games, Bugs Bunny, Crazy Castle, and Genghis Khan. We chose these games because of their contrasting degree of structural variance in these levels. For Genghis Khan, it has mostly plain tiles, but with different colors. Whereas for Bugs Bunny Crazy Castle, it has high structural variance, but the brick style, which was used as a solid which was used in solid context for Super Mario Brothers, is used as a background here. So we were testing out the edge cases, and these are the good and the bad examples of generation. So the bad examples show presence of unreachable structures or repeated patterns. For Genghis Khan, it showed abrupt breaks in level generation, or multiple pairs of towns and castles, whereas the original data set had only one. The good examples showed style similar to that of its original data set and were more structured. So for quantitative evaluation, we employ expressive range analysis on tile-based metrics. And on Bugs Bunny Crazy Castle, we find that it covers a good amount of generative space, and the generations are slightly skewed, just like the original data set. Overall, we find the levels have moderate interestingness and density and low linearity. In comparison to this, if you look at Genghis Khan, it covers less amount of generative space, but we still find this result heartening because Genghis Khan is a turn-based strategy game and not a platformer game. So this shows the ability of our approach to work generally for different domains as well. Next, it is important to learn where our pipeline would fail. And we find that clustering is important part of our pipeline because for Genghis Khan, where the tiles lacked structural variance, the clustering was very random, and therefore the LSTM did not do a good job at generating the levels. To improve this, we suggest avenues for learning more robust representation by employing other architectures like VQVAE or GMVAE. We also find that application of tile embeddings for other PLGML tasks such as level blending would be an interesting work. With that, I thank you all for joining this session. If you have any questions, I'll take.